Physics Lecture 10, Atomic and Nuclear Phenomena. This seems like a subject we would go over in general chemistry, but we will visit it in the physics portion as well, particularly dealing with the photoelectric effect. This is when light of a sufficiently high frequency is incident on a metal in a vacuum. This will result in the metal emitting electrons. Remember from our electrostatics and magnetism unit that any sort of movement of current will result in a magnetic field. Current, if you remember, is the movement of electrons, even though it is noted as the movement of protons. The threshold frequency is talking about the minimum frequency of light that will cause the ejection of electrons. The equation is noted as E equals hf, or energy equals Planck's constant times the frequency of the light. This revolves around the premise of photons, or integral numbers of light quanta. The energy of each photon is noted by this equation. Now that we've talked about what the photoelectric effect is, let's go into some kinematics regarding the electrons. When the electrons are ejected, their Kmax, or their maximum kinetic energy, is noted as hf minus w, or Planck's constant times frequency minus work. Work is noted as W equals hft. Now, if you don't remember, Planck's constant equals 6.626 times 10 to the negative 34 joules seconds. It's not guaranteed that this value will be provided to you on the MCAT, so make sure you have this committed to memory. Nuclear binding energy and mass defect. This equation is actually very famous, and many of you probably recognize it. It's the equation that Einstein famously discovered, E equals mc squared, or, more simply stated, mass is energy. There's a lot of implications to this, and this theory is commonly considered one of Einstein's crowning achievements, but it simply equates that mass and energy are one and the same. Nucleons are protons and neutrons, anything that is within the nucleus. They are held together in the nucleus by binding energy. This is a very strong force that holds it together. If you recall from electrostatics, you remember that like charges will repel each other, so having all these protons in close proximity held so tightly would require an extremely strong force. There is a question that I'm sure many of you are asking right now, though. Why is it that electrons don't just fall into the nucleus? Well, they're held together by a very interesting mechanic, and that mechanic is not very well understood. Suffice to say that electrons do not obey traditional movement. Now that we've gone over some fundamentals, let's go into the absorption and emission of light, which will govern most of this lecture. Absorption is when a photon is taken in, leading to an excited state. So if I were to have my nucleus and a electron here, and this will be the simplest atom, or hydrogen. When a photon hits this in the ground state, the electron will jump to an excited state, so it'll go up to a higher orbit. Emission, on the other hand, is when a photon is emitted, leading to a lower energy state. So, if we were to go back to our hydrogen atom, with our electron listed here, if the electron were to jump back down to a lower level, the result will be a return to a lower state. In the case of hydrogen, this would be the ground state, leading to the emission of a photon. For this little portion, let's go into common applications of absorption and emission. Below are some emission spectrums and absorption spectrums. For the purpose of studying matter, it is a very useful tool to look at the absorption and emission spectra of the compounds of interest, starting with infrared spectroscopy. This uses absorption wavelengths to determine bonding structure. This is possible because different bonds will absorb different wavelengths of light. Below is a very classic IR spectroscopy result. As you can see, there are a couple areas that we can go into, starting with this peak right here and this peak right here. If you feel like testing yourself, see if you can remember what peak corresponds to what, and try to take a guess at this structure. If you don't remember, that's okay. Just refer back to the organic chemistry module. UV vis spectroscopy uses light in the visible and the UV range to identify compounds. And a display of this data is listed to the left. The visible spectrum is noted on the right. If you talk about the visible spectrum and the UV range, we are talking about this area all the way down. The IR spectrum is for IR spectroscopy. Fluorescence. When a fluorescent substance is excited, it'll glow with visible light. If you've seen a neon sign, you will have seen fluorescence at work. On the right are some colors that you can get from the fluorescence. On the left is an example of a lab experiment where the fluorescence intensity is measured. For this little bit, let's go into some common nuclear reactions, especially the ones that you're going to have to know on test day. Before we begin our discussion of nuclear reactions proper, let's go into some isotopic notation and two basic reactions that I'm sure we're all very familiar with at this point. Isotopic notation is how you note the isotopes for the given atom. As you can see, the convention for it is listed below. Fusion is the combination of smaller nuclei into a larger one, whereas fission is the splitting of larger nuclei into smaller ones. Currently, the only energy we can harness is from fission. However, fusion research is currently a very hot button issue in scientific research. Radioactive decay. There are several types of radioactive decays that you are going to have to be able to recognize on test day. The first is alpha decay, or the emission of an alpha particle, or just a helium atom. The convention is listed below. Anytime you see the equation listed in this structure, you can assume that there is some sort of alpha decay occurring. Next up is beta decay. This is the emission of an electron. You will note that the mass doesn't change, but the charge will. This can also be positive, so take note of that. The other two that you will have to be able to recognize are gamma decay, or the emission of gamma rays, and electron capture, which is the absorption of an electron. If you're a comic buff like me, you'll know gamma radiation is the reason why Bruce Banner changed to the Hulk. The last thing we're going to discuss is exponential decay. The most famous example, and the one that you will likely be tested on the MCAT, is half-life. This is the time it takes for half of the sample to decay. Most of these samples will decay into some amalgamation of compounds and lead. There is a very, very intricate equation to solve this. However, usually it's much simpler for the test to just simply take the mass and half it over the time that it's allotted. Exponential decay is listed below, and the decay constant lambda is listed as well. That'll cover it for our discussion of atomic and nuclear phenomena. Make sure you have a good grasp of this, and study hard, and you'll be sure to do well when it comes time on test day. Please join us in the next lecture.